This section is on sensory systems. I'm going to start by talking about hearing using sensory hairs. Here's a sensory hair sticking out from the surface of an animal. It is a stiffened structure, hair-like in some sense. If it's invertebrates, it could be something like chitinous in a vertebrate. It could be keratin. Here's a sensory neuron that has stretch channels, so sodium stretch channels that will be opened in response to these pressure waves. So pressure waves are areas where there are more densely packed molecules and they're moving, they're pushing against each other, and eventually they hit as a small pulse of air against the hair, and it causes bending of the hair. So each pulse will bend it over and then bend back in between the high pressure parts of the wave, and each bend opens, and then as the hair moves back slightly, closes sodium stretch channels in the sensory neuron. So we get a pattern of opening and closing. And let's imagine that it's a 50 hertz sound, in other words 50 pulses per second. Then we'd have 50 pressure waves per second, and we'd have 50 action potentials per second. So how would you detect whether there were 50 versus 60 or more action potentials per second? What kinds of neural circuits would do that? Well, let's say that B fires only if it's receiving 50 action potentials per second. In other words, 50 pulses of neurotransmitter in each second causes it to start firing action potentials. That means B will fire if there are at least 50 neurotransmitter pulses per second. In other words, Hertz 50. And now imagine another interneuron C that requires 60 pulses of neurotransmitter. In other words, temporal summation from 60 pulses of neurotransmitter. And it won't fire action potentials if there are fewer than 60, but it will fire action potentials. C will fire action potentials if there are more. So let's imagine that interneuron B is firing, but C is not. Then that must mean that the sound is about 50 hertz, 50 cycles per second. Hairs can be used to detect sound frequencies, pulse frequencies, of up to about 1,000 per second, 1,000 hertz. Mammalian ears detect up to about 20,000 hertz, and that requires a different mechanism. No neuron can produce more than a maximum of about 1,000 action potentials per second. And so in the mammalian ear, it's the location of an event that tells you what the sound is. So the cochlea is this snail shell shaped structure, and it's got a double membrane, 2 cell layers, and between those 2 cell layers in the middle are mammalian hair cells. Pulses of sound come into this rigid structure through a window, cross the membrane at a particular location depending on the frequency, and then exit through the only other flexible part of the cochlea. So the path of the pressure wave coming in through the one membrane has to cross the central pair of membranes, past the hair cells, and go out of the other membrane. So here's a cochlea flattened out showing a series of hair cells, and high frequency sounds only cause movements of the membrane near the 2 windows. Low frequency sounds cause movements of the membrane out near the tip. In a human ear, that's about 20 hertz. The reason for the difference is that the membrane is thin and flexible at one end, and that thin and flexible nature of it allows it to bend rapidly in response to frequent sound pulses. So high frequency pulses set up a resonant movement at the end near the 2 windows. The membrane is thicker and more rigid at the far end, and so it bends slowly, and so low frequency sounds cause it to bend. So the location indicates the frequency. How do the individual hair cells work? They have little individual structures that look like hairs, but they're just actin stiffened membrane structures that project out from the cell. So they're called hair cells because they look like they have hairs. Pressure waves coming in from one side push across these, and if the membrane is bouncing up and down on top of these, it pushes these from side to side, so either a pressure wave or a membrane. They open stretch channels when they're bent in one direction and close the stretch channels in the other direction. So opening them allows a pulse of calcium in and results in neurotransmitter release to a neuron. So looking at the cochlea again, the location indicates the frequency of the sound. Remember, high frequency sounds at one end, near the two windows, and low frequencies at the others. So each hair cell would have a neuron coming from it, and if there's an action potential in A, then the frequency would be 20,000 hertz. If there's an action potential at E, 20 hertz, and spread out across the length of the cochlea are different sound frequencies. So how do you detect combinations of frequencies? Well, imagine interneurons. Here's interneuron F, and it's depolarized 15 millivolts by an action potential from A and an action potential from C. The result will be that if there are action potentials in F, that must mean there's a sound combination of 20,000 and 1,000 hertz. So again, here are different hair cells. The ones closest to the two windows would be for low frequency sounds. And imagine a neuron G that is getting neurotransmitter from all three with 10 millivolts from each depolarization. If G is firing action potentials, that will happen only with a combination of sounds of 10,000 very high frequency, 1,000 medium frequency, and 20 low frequency. How do you tell that one sound follows another? For example, a low frequency sound following another. What I'm drawing here is an input that has a long, thin, squiggly axon from C. We have two hair cells that are getting movements in response to 1,000 and 200 hertz, respectively. Each one depolarizes D 15 millivolts. We'll get an action potential in D only if there's a 200 hertz sound, which is going to take time for the action potential to get from B to C to D. And that sound of 200 hertz is followed by a sound of 1,000 hertz. So the 1,000 hertz has no delay. The 200 hertz has a delay. They arrive at D at the same time. So first the 200 hertz sound, then the 1,000 hertz sound, and they get to D at the same time, causing an action potential.